Okay, hi everyone. Today we'll be taking a look at a question on graphing techniques. So in this question, we are given y equal to fx shown here. The graph has a turning point at A, which is minus 1, 4, the y-intercept at 0, 6, B, and point C, which is the x-intercept minus 3, 0. So the lines x equal to minus 2 is the vertical asymptote and y equal to 10 is the horizontal asymptote. So the objective of this part of the question is to draw the graph of 1 over fx, which is the reciprocal graph. So first thing first, actually a lot of students are very confused that 1 over fx is the same as the inverse curve. In fact, they are not the same. So for 1 over fx, you are actually doing a reciprocal for all the y values you see on the graph. As for f inverse x, which is the inverse curve, is a reflection of the original curve about the line y equal to x. For this, f inverse graph is predominantly found in the topic on functions. So they are not the same. Right, first thing first, before we will be drawing the graph of 1 over fx, there are certain key features that we would like to analyze first before drawing. The first features that we want to look at is the asymptotes of the 1 over fx curve. To find the asymptotes, right, the first thing we will want to look at is the x-intercept. Because at the x-intercept, the value of y actually is 0. So when you do a reciprocal of 0, it's actually 1 over 0, which is undefined. So you will become a vertical asymptote. So we will have one x-intercept here, x equal to minus 3. So there will be one vertical asymptote, x equal to minus 3. All right, there are no more x-intercepts, so that's the only vertical asymptote. The original graph has a horizontal asymptote at y equal to 10. So when you do a reciprocal of y equal to 10, you will get a new horizontal asymptote at y equal to 1 over 10. Right, the second thing we want to look at is the intercepts of the 1 over fx curve. So the first thing that we look at is the vertical asymptote. So when you have a vertical asymptote, part of the curve will actually tend to a very large y value or a very large negative value of y. So at this point, imagine you have a very large value of y, which is like minus 1 million. So when you do a reciprocal of it, you will get close to 0. Likewise, a very positive value here, maybe 1 million. Reciprocal of 1 million is very small, which is close to 0. So therefore, if you have a vertical asymptote, you have a new x-intercept at that point, which is at minus 2, 0. So this question, they gave us the y-intercept. So when you do a reciprocal of this particular point, you will actually get a new y-intercept at 0, 1 over 6. The third thing we want to look at will be the turning points. Alright, so we have actually one turning point here. When you do a reciprocal of this particular point A, minus 1, 4, you will have a new turning point at minus 1, 1 quarter. So in this case, it's a minimum point. So when you do a reciprocal, you will have a maximum point at minus 1, 1 quarter. So maximum. Alright, take particular note when you have a turning point which happens to touches the x-axis. This will not give you a new turning point when you do a reciprocal curve, because at this particular point, the value of y is actually 0. So when you do a reciprocal, it's supposed to have a vertical asymptote, like this case here. So once we have all these key features in place, we can try to sketch the graph first. So the first thing we put in will be the asymptote x equal to minus 3. So we have one vertical asymptote x equal to minus 3, one horizontal asymptote at y equal to 1 over 10. So intercept is at minus 2, 0, which is this point here, minus 2, 0. There will be one y-intercept at 0, 1 over 6. It will be somewhere here, which is larger than 1 over 10. So it's 0, 1 over 6. And we know we will have a turning point at minus 1, 1 quarter. So minus 1, 1 quarter will probably somewhere at this particular point here. So it's minus 1, 1 quarter. Right, so with all these things in place, now we will attempt to sketch the graph by analyzing some of the endpoints. This point here, this point here, this point here. Let's go through step by step from left to right. So at this particular point, it's slightly less than 10. So when you do a reciprocal of slightly less than 10, you will get slightly more than 1 over 10. So you will get somewhere at this particular point. So as this one tends down to close to 0, so imagine at this particular point, it's a very small value of y, probably like 0.00001. So when you do a reciprocal of it, you will expect to get a very large values of y at this particular point, slightly above the x-axis. So you get somewhere here, right? So knowing that, right, as this one tends down to close to 0, this one will tends up to close to infinity. After crossing this x-axis here, at this particular point, is a very small value of y. Like for example, minus 0.00001. When you do a reciprocal of a very small y value, you will expect to get a very large values of y, which is somewhere here. As this one tends down to a very large negative, this one will actually tends up to a very small value, right? So we are done with this part. Now let's move on to this part of the curve. So here is a very large positive. When you do a reciprocal, you will get a very small positive. Remember, you are only doing reciprocal to all the y values. The x value will remain unchanged. So at this particular point, which matches this particular point here. So as this one tends down to a minimum value, this will in fact tends up to a maximum value somewhere here, right? So this point will correspond to this point. So maybe I can call it a prime. As this one turns, this one increases, and it will cut the y-axis 0, 6. So the reciprocal will actually cut the graph at 0, 1 over 6 here. As this one continues to increase, it will tend to y equal to 10. So for reciprocal curve, you will tend to 1 over 10 instead. And it should be slightly above the horizontal asymptote. This is below, so this is above. All right, so maybe we can call this B prime. Right, for C, we can't label it because it has already turned into a vertical asymptote. Right, so this will be my graph of y equal to 1 over fx. Right, so let's move on to the next part of the question, which says you are supposed to draw the graph of y equal to f prime x, which is the gradient curve. Right. Right, similarly for gradient curve, we will like to analyze the key features first before attempting to sketch a graph. Right, so the key features for a gradient curve, right, is first thing, also the asymptotes. Right, the first thing that we will look at will be the vertical asymptote. For the original curve, they say x equal to minus 2 is the original vertical asymptote. Right, the definition of vertical asymptote is the value of x that causes y to be undefined. So if it's undefined for y equal to fx, so it will also be undefined for the gradient curve. So again, we will have a vertical asymptote x equal to minus 2. As for the original horizontal asymptote y equal to 10, you can in fact see for any horizontal asymptote, the graph, when it tends to it, the graph will approaches like a straight line. So that means to say the gradient of this particular part here, will actually tends to 0. So for any horizontal asymptote, we will have a new asymptote at y equal to 0. Right, second thing, we will take a look at the intercepts. So intercepts, right, can be obtained by looking at the turning points of the original curve. Because for turning points, right, the value of the gradient there will actually be 0. So like this point here, the gradient is 0. So any more? So no more. There will be just one x-intercept for the gradient curve, which happens to be at -1, 0. Right, as for the point B, some students will ask, what happened to the y-intercept? So the thing that we can actually ignore it because the value of the gradient here is not being defined for us. So we won't be able to figure out what is the value of the gradient at this particular point here. Right? But we know that this is a positive gradient. So there will be only one x-intercept at -1, 0. Right. So the third thing, right, is we will analyze the gradient of all this curve here. So what do I mean by analyze the gradient? Because when we are looking at this, there are certain parts that is a negative gradient, certain parts that is a positive gradient. Right? The best way of drawing the gradient curve, which I feel that maybe you can kind of like visualize you are a person standing here. So it's like you are going for a hiking expedition along a mountainous area whereby there's a series of peaks and valleys. Sometimes you are climbing up, sometimes you are descending down. So as long as you imagine that you are ascending, it's considered as a positive gradient. When you are descending, you consider it as a negative gradient. So the steepness of this slope, right, will correspond to the magnitude of the gradient. So the steeper the slope is, the larger the magnitude it will be. So let me just illustrate how to visualize this by looking from left to right. So the first thing first, we will again try to put in the key features on the graph first. So the first one will have a vertical asymptote x equal to -2. So let's draw it first, x equal to -2. And we will have a horizontal asymptote at y equal to 0. We will have one x-intercept at -1, 0, which is somewhere here. So -1, 0. All right. So let's imagine you are standing here. At first, it's like almost flat. As you proceed more to the right, you can see that you are falling down faster and faster and faster. But for this part of the curve, you can see that it's actually negative gradient. So negative gradient actually will always be above the x-axis when you draw the gradient curve. So initially, it will have a very small negative value. As you proceed more and more, the gradient will get more and more negative until at this particular point. So when you translate it into the graph of the gradient curve, so initially it should be slightly below the x-axis to show that it is a negative gradient. So as you proceed more to the right, this will actually go down negative and negative and negative until somewhere here. All right. So now imagine you are standing at this particular point here. So at this particular point here, for this stretch, you can see is a negative gradient. So it will be all entirely comprising below the x-axis. As you proceed more to the right, at first you are actually descending at an extremely fast rate. Right? This is very steep. So it will be somewhere here. So as you proceed more to the right, then you reach a point where it's 0 gradient, which is somewhere here at this particular point. After this particular point, you can see that you are in fact ascending the slope. So initially, when you ascend, it's pretty easy. So it's very gentle, the slope. As you proceed more to the right, you can see at some point along here, you in fact reach the maximum positive gradient at this particular point here. Right. Let me just, maybe I will just enlarge this portion here. So initially it's very easy to climb. As you proceed more, at this particular point is the steepest. So at this particular point, you expect to get the most positive gradient, right? And you will go somewhere until this point. So this point here, maximum positive gradient, is correspond to this point, which is this point. Another name for it is called its point of inflection. But at this point in time, you don't have to worry much about this. So as you were proceeding more to the right, you can see that you are still climbing up, so it's positive gradient. As you ascend, the gradient gradually decreases until it approaches 0. So it's still positive gradient, then it will slowly go down until close to 0. This point here, we won't be able to label it because we won't know what is the value of this particular gradient here. All right, so let's see, maybe we can just label some of the points here. So we will have, okay, so if you want, actually, you can label this as a prime prime, right? The rest of the points, the original point, we won't be able to label it because we will not know what is the value of the gradient there. All right, so this will be the graph of y equal to f prime x. Okay, so let's take a look at the part B of the question, which is not related to the original part of the question. Okay, so this part states the sequence of transformation that will transform the ellipse of 4x squared plus y squared minus 4y equals 0 to a unit circle. Right, the meaning of unit circle basically means it's a circle with radius of 1. Okay, so we can just erase all this again. So the equation is given by 4x squared plus y squared minus 4y equal to 0. So we are supposed to describe a sequence of transformation that will transform this into a circle of units radius. Right, when questions are asking you to state a sequence of transformations, basically they are just asking you to do some description of the transformation, which will include translation, scaling, or reflection. Right, so my approach for this question, probably first, I may want to do a completion of square for the y part, because I think the final result is only comprising of only one y. So it will be slightly easier if you just combine this into one single value of y term. Right. So here I will just do a completion of square for this part. So I will get y minus 2 square minus 4 equal to 0. So shifting this constant term to the right hand side, I'll get 4x squared plus y minus 2 square equal to 4. And I will do a division of 4 throughout. I get x squared plus y minus 2 square equal to 1 over 4. So probably, maybe I can just shift this term into the square. So I will get y minus 2 over 2 square equal to 1. So my final result I want to obtain is x squared plus y squared equal to 1. So by a bit of observation, I can see that actually I'm only doing transformation for the y direction. Right, so the first thing probably I will attempt to do is to do a replacement of y with y plus 2. So when I have x squared plus y minus 2 over 2 square equal to 1. So when I do replacement of y with y plus 2, I will get y over 2 square. Right, so replacement of y with y plus 2 basically means is translate 2 units in the negative direction of y. Basically means you are like shifting the entire curve down by 2 units. So the next step I will attempt to do is to replace my y with 2y. So I will get x squared plus y squared equal to 1. So replacement of y with 2y basically means is scaling in the y-axis by half units. Scaling half units in the y-axis. Right, so there we have it.